So if we let x of t is the random process, then we define expectation of x of t. The mean value of the random process. So this is denoted as mx of t. Sometimes we may represent the same as mx of t. Either way can write. So here it is depending on the time. For example, if t equivalent to t1, you will get mx of t1. T is equivalent to t2, you will get mx of t2. So this mx of t1 may be different from mx of t2. In the case of random variable, we simply represent it as mx. So it is a constant forever. But here, the mean value of the random process is depending on the time. Because if the time is changing, if the time instant is changing, the values that are taken by the random variable also changing. At t equivalent to t1, we have the random variable x of t1. It has one mean value. At t equivalent to t2, the random variable is x of t2. So in that case, the mean value may be different from the first mean value. So that's why we represent that as mx of t. Expectation of x of t, the definition is same again. In the case of random variable, we define it as expectation of x. So the random variable x here, x of t is a random process. Okay. Strictly speaking, at t equivalent to some tk, okay. That is, if you let, we are observing the random process at t is equivalent to tk, then this can be written as expectation of x of tk is equivalent to mx of. So this can also be written as. So these two notations are same. Either you can represent the mean value by mx of t or mx of t. Either way. So here this can be written as integral minus infinity to plus infinity. This is x of tk. Is it right? Because expectation of g of x, expectation of some function of something. Okay. So we write it as minus infinity to plus infinity x of tk. Here fx of tk and xk. This is dx, or you can also write dxt. Either way you can do. So what is this fx of tk of x of k? This is the marginal probability density, is it? Because x of tk is the random variable obtained by observing the random process at t equivalent to tk, is it? So therefore, this fx of tk of xk indicates the marginal density, is it? How can you obtain the marginal density? We represent the joint PDF as fx of t of x, is it? Where x of t is equivalent to the matrix x of t1, x of t2 and so on, x of tk, and this x is another matrix, that is x1, x2, so on, xn, column matrix. Okay. So here fx of tk of x of k. So x of tk is the random variable obtained by observing the random process at t equivalent to tk. What is xk? Xk is the values that are taken by the random variable x of t. So therefore, this indicates the marginal density function of the random variable x of t, whereas this fx of t of x, this indicates joint probability density function of all the random variables x of t1, x of t2, x of t3 and so on, x of t. Understood the difference? So that's why here we are writing this as minus infinity to plus infinity x of tk fx of tk of x of k dx. Or otherwise, if you let x of t is the random process, and the small x of t is one sample function of the random process. Small x of t is the one sample function of the random process. Capital X of t is the random process itself. Then the mean value of this can be written as mx of t is equivalent to expectation of x of t, that equivalent to, say, minus infinity to plus infinity. This is x of t fx of t of x dx. Is it right? See, in this case, what we are writing, we are simply minus infinity to plus infinity. This capital X is replaced by small x, fx of x dx. This is in the case of random variable. But here, this is the mean value of the random process. See, this x of t, capital X of t. Here we have written small x of t. If you let x of capital X of t is the random process, small x of t can be considered as the values that are taken by the random process x of t. Okay. So here, the small x of t is called as the sample function. So letting x of t, small x of t is one sample function, capital X of t is the random process, then the mean value can be written as minus infinity to plus infinity x of t fx of t of x dx. See, this is the mean value of the random process at t equivalent to tk. So this is the mean value of the random process for any t. Here if you replace this t with some other value, then you will get the corresponding mean value at that particular time. In the case of random process, the mean value is depending on the time. So that's why we represent it as a function of time, mx of t or mx of tk. Normally, if you consider the tk is particular value of the time. So at that case, you will get the constant. Mean value is constant. But if the time is varying, mean value may vary. The random process is defined by x of t is equivalent to a cos omega naught t plus theta. A cos omega naught t plus theta, where a and theta are independent real random variables, comma, theta is uniformly distributed, over the interval 0 to 2 pi. Theta is uniformly distributed over the interval 0 to 2 pi. Find the mean value of random process. Assume omega naught is a constant, omega naught is a real constant, and x of t is equivalent to a cos omega naught t plus theta. A cos omega naught t plus theta is a sample function. X of t equivalent to a cos omega naught t plus theta is a sample function. See, this is a random process. One sample function is given by a cos omega naught t plus theta. So how can you do this? The mean value of the random process is mx of t This can also be written as mx of t, which is equivalent to expectation of x of t. Is it? So this can be written as expectation of a cos omega naught t plus theta. See, capital theta is the random variable. Independent. See, here this is omega naught is constant. So theta is the random variable. A is the random variable. So therefore this can be written as expectation of A into expectation of cos omega naught t plus theta. Since A and theta are independent, A and theta are independent random variables, is it? Here omega naught is a constant. T is not the random variable, therefore only the random variables are A and theta. So therefore, but A and theta are independent. So we can write expectation of A into expectation of x. Consider this expectation of cos omega naught t plus theta. We try to evaluate this. This is equivalent to minus infinity to plus infinity cos omega naught t plus theta f theta of theta dt. So what is f theta of theta here? It is the probability density function of the random variable theta. Theta is uniformly distributed from 0 to 2 pi. This is equivalent to 1 by 2 pi for 0 to is that right? And 0 otherwise. Theta is uniformly distributed over the interval 0 to 2 pi. So therefore, this is 0 to 2 pi. So 1 by 2 pi can be taken out. Cos omega naught t plus theta d. So this is equivalent how much? So area under cosine over a period is 0. So therefore this value equivalent is. So integration should be with respect to theta, not t. We are not integrating with respect to t. We are integrating with respect to theta, because theta is the random variable. So therefore mx of t is equivalent to 0. That is irrespective of the distribution of the A. Here we don't know how the A is distributed. That is not, nothing is mentioned about. A is a random variable. So it is E of A into some 0. You will get. So now we consider another parameter, the correlation. Let x of t is a random process and we observe this random process at t equivalent to t1 and obtain the random variable x of t1. Observe the random process at t equivalent to t2 and obtain the random variable x of t2. We obtain two different random variables x of t1 and x of t2 by observing the random process x of t at t equivalent to t1 and t equivalent to t. We have two observation intervals or two observation times instance t1 and t2, and we obtain two different random variables x of t1 and x of t2. So here the difference between the t1 and t2 is very small. Then the correlation between these two is more, almost similar. But if the difference between t1 and t2 is increasing, definitely dependence or the similarity between these two random variables may vary. For example, let this is a random process. If you observe the random process here and observe the random process immediately after that, so the difference is very small, or the difference between the two random variables is very small. But if you consider, you observe one random variable here, observe one random variable here, or observe the random process at two different time instants t1 and t2. So obviously the random variable that obtained, take for example this is another sample function like this, is completely different from this random variable. The random variable obtained here may be different from the random variable obtained here. Is it right? This is the random process. We are observing the random process at two different time instants t1 and t2 and obtain two random variables x of t1 and x of t2. Definitely there may be some interrelationship between these two random variables. Okay, that is, we can study this particular random process by measuring the various parameters that indicate the interrelationship between these random variables. Here the random process is same, but we observe the random process at two different time instants and obtain two different random variables. So definitely there may be some interdependence between these two random variables. So that can be evaluated by finding the correlation function or the covariance function. The correlation of these two random variables x of t1, x of t2 is defined as, see, what is the correlation between the random variables x, y? It is expectation of x, y. This is one random variable, this is another random variable. So we call it as the correlation and we denote it as rxy. The same manner, the correlation between the two random variables x of t1 and x of t2 is the expectation of x of t1, x of t2, and we denote this as rxx of t1 comma t2. See, here we have rxy, that's why we have written xy, but here we have xx, so that's why we have written rxx, t1, t2. What is the difference between this and this? Here it is not depending on the time, here it is depending on the time. So this is the notation of correlation of x of t1 and x of t2. But if you consider the two random variables x of t1 and x of t2, they belong to the same random process. So that's why this quantity is called as autocorrelation. So this is the correlation between two different random variables. This is also the correlation between two different random variables, but these two random variables belong to the same random process. That's why this is autocorrelation function of the random process x of t. The autocorrelation function of the random process x of t is given by Rxx of t1 comma t2, that is equivalent to expectation of x of t1, x of t2. So here, if you let the time difference or the difference between these two observation instants is tau, then this can also be written as expectation of x of t1, x of t1 plus tau. Is it right? That is t2 is equivalent to t1 plus tau. And this can also be written as expectation of x of t and x of t plus tau. Here I simply eliminated the subscript, nothing is there. I removed the subscript. Now if you substitute t is equivalent to t1, x of t1, x of t1 plus tau. If t equivalent to t2, x of t2 plus t2 plus tau. That is, x of t is the initial, the first time instant, t plus tau is the next instant, and the difference between these two is tau. Therefore, instead of writing x of t1 plus tau, we can simply write x of t into x of t plus tau.